All right, guys. Can you guys hear us good?
Yes, sir.
Alrighty, thank you. All right, I'm Justin. I'm the treasurer of IEEE.
And I am Kevin. I'm the secretary of IEEE.
Alrighty, today we're presenting this basic circuit knowledge workshop. So we're just going to be going over some casual stuff that you'll most likely learn in 211. So we'll be going over the different kinds of sources we got to work with, resistors, inductors, capacitors, voltage, current. Shouldn't be too hard. Feel free to jump in on any questions you guys have. We'll try and answer them to our best. And yeah, let's get started. So the topics. All right, Kev.
So the first thing we got are sources. So the different types of sources that you'll typically see in circuits are independent sources, dependent sources, DC sources, and AC sources. So independent sources, what that means is that it has the ability to generate either voltage or current on its own. So aka, independent. Dependent, the sources will depend on something else within that circuit. So what that means is sometimes you'll see like on your problems, there's going to be a dependent source, and you'll know it's dependent because it's going to be in the shape of a diamond, and it'll have like a little equation underneath it saying like 4V naught or 4 I sub C. So basically, you don't know that value. That value will change, and it varies depending on another element within that circuit. So the next would be DC sources. DC stands for direct current. And so DC sources allows the current to only flow one way inside of that circuit. Now AC stands for alternating current sources. So with AC sources, if we use a sinusoidal wave, basically like, we took calculus, so sine and cosine as so that graph. So basically that's that alternating current source. It's gonna go forward and backward. And with that being said, yeah, that's the difference in sources.
All right. So now we got to account for voltage. So voltage is the measurement. Well, the measurement for voltage is volts, and you can denote it with a capital V. And usually 1 volt is equal to 1 joule per 1 coulomb. So we can say J over C. And you should have probably learned this in your 152 physics class. And the way we calculate voltage is typically using Ohm's law, where we got V is equal to IR. So voltage is equal to the current times the resistance. So what voltage represents, it's the force pushing the charges throughout the circuit. So in our next slide, we'll learn about current, and current is the flow of charges, right? So this voltage, voltage's purpose is to push those charges throughout the circuit. And throughout EE, you'll hear different names for voltage, such as potential difference or electric motive force, aka EMF. And if we use a water analogy for voltage, so voltage in this case would be gravity. It's the force pushing the water throughout the piping, and this water would be we'll symbolize it for our current. So voltage, aka gravity, is pushing the water, aka current, throughout our circuit.
So the next thing that we got is current, and the it's going to be denoted as I within electrical engineering. So the unit is going to be amps. Amperes long. That's the guy's last name, but amps. So the calculations for that is just Ohm's law. Voltage is equal to current times resistance. That's going to be very, very important in electrical engineering. It's like the foundation of everything, Ohm's law. So just going to manipulate that equation to get current is equal to voltage divided by resistance. So what is current? Current is the flow of electrons across a cross-sectional area per second. So conventional current direction. So with conventional current, you're going to learn about passive sign convention. Passive sign convention means if you look at this circuit to the right with the pointer, so you see how there's the positive polarity and then the negative polarity. So basically with passive sign convention, the current is going to flow from the positive side to the negative side. And that's how that works. But this little bit that we added for the electron current. So in reality, so what happened was the guy who created, who learned about currents and put it out there, he went with the passive sign convention. It goes from positive to negative. But realistically, protons cannot move, only electrons move. So it's actually going in reverse polarity. It's actually the electrons moving from negative to positive. But that's going to mess you up. That's just kind of like a nice little side information on your homework problems and in class, all the circuits that you deal with. Remember that passive sign convention, the current flows from positive to negative.
All right, I think we have a question. So
Let's hit it.
Let's see. Damn, where is it?
Oh no, that's the pointer, bro.
There we go. All right, chat. How did you get that pointer? That's sick. Michael, I just went on my presentation and I went down here and clicked pointer. See? So now I got the pointer. All right. So
And,
next slide.
Justin,
my
did you
bad.
want to hit the did you want to hit the water analogy for current?
Oh yeah, my bad. So we're gonna be using the water analogy a lot for this workshop. So our water is just basically gonna represent our current flowing in a circuit, but instead we're having water flowing through piping. So this water is our current and it's coming out. So basically the water in here amount as the water in here, it's just different amounts flowing in, but all the same, they're equal. So we're gonna take a look at resistors really quick. So resistors, the units for resistance is ohms, denoted by this symbol right here, the ohm symbol. And once again, we use Ohm's law to manipulate, to solve for resistance. So we start with V equals IR, and we manipulate it to where R is now equal to V over I, voltage over the current. So what resistors do in a circuit is they just resist the flow of current. So they try and, I want to say like, kind of like fight back. So if you look at this little drawing right here off to the right, we have Ohm's law. We got voltage pushing current through a little tight tubing, while resistance is trying to enclose that tubing to only allow a little bit of current flow through rather than the whole thing. So if we look at the water analogy, so we already know about our voltage. Our voltage is the force of gravity. Water is our current. So now we take a look at the piping, the structure of the circuit, right? So without any resistance, the current is able to flow through. The water is able to flow through without any drawbacks per se. But if we kind of thin out the piping, we got less current flowing through in this area, and it's a lot harder. So there's more pressure needed to get the current to flow through in here, the water to flow through in here. And yeah, so resistance, in summary, resistance just impedes the flow of current. And this is what a resistor looks like in reality. And we sometimes use this resistor guide to help us solve for the resistance on different resistors. It's a little harder to kind of read this. So I personally just use a multimeter to give me my resistance value, but Kevin knows how to use this pretty well. So Kev, do you want to go over it?
Yep. So basically, that's what the resistor is going to look like. When you take a look at it, you'll see those colored bands. And so with those colored bands, if you check out those arrows, so the far left, right there, it goes up, they have significant figures. So you see the first one, it is orange, so it's 3. Second one is red, so it's 2. And then the last one is brown, so it is 1. So just think about the number 321. And then the next colored band is going to be your multiplier. So if you see that arrow goes up to, it says multiply by 10. So 321 times 10 is 3,210, aka 3.21 kilo ohms. And if you look to the right side, it says 3.21 kilo ohms. And so the problem with this typically is, I had the issue too, is how do you know which side is left, which side is right? So when you look at it on the right side, it has less bands than the left side. So that's how you orient it. You know that the side with more bands, that's where you're going to be starting at. And that's how you read with that graph.
Right. So next, Kevin's gonna talk about capacitors.
So over here we got capacitors, and the unit it goes by is farads. So the calculation is going to be I is equal to C dV dt, or V is equal to I over C integral of I dt. So basically you'll learn that in 211. That's another reason why you do need differential equations and linear algebra before taking 211, because you're going to be messing with a lot of differential equations and integrals. So a capacitor is used to store energy in an electric field within a circuit. And the next thing we're going to be talking about is dielectrics. So dielectrics is an insulator inside a capacitor, and it's used to increase the capacitance of a capacitor without increasing the size of the capacitor. So what that means is we're going to go over, I guess, how a capacitor is made. So if you look at a capacitor, it's got two plates, and between these two plates is going to be an electric field. And so it's going to store that electric field as energy. And what happens is, I don't know if you guys remember physics, but the further away these plates are, the weaker that electric field is. And the closer it is, the stronger. So basically what they do is they have these two sheets, and then it's creating that electric field. And then they have like, and they have an insulator in between. It kind of looks, it's just like a really thin piece of paper, it kind of looks like, and they just slap it. So it's kind of like a sandwich thing. So they slap it, you got a sandwich basically, two sheets, and then an insulator in the middle. And then they kind of roll it up. And then after they roll it up, that's why you get this capacitor looking guy where it's like a cylinder. So that's how they create these capacitors. And the next thing is capacitors in steady state. So what that means is that the source is DC. So in steady state, again, we just talked about DC source and AC source. When a capacitor is connected to a DC source, it's just going to act as an open circuit. And
Yeah. So so in steady state, the capacitor really won't do much. Instead, it causes that open circuit, so no current will be flowing through where that capacitor is at. So now if we take a look at the water analogy, we're going to be using this water valve as our voltage. The water's still going to be our current, but this storage container is going to be our capacitor. So when voltage is on, or the valve is turned on, it's going to pour water in here and have it dissipate at the end of this piping right here. But as water is flowing through, it's going to fill in this tank until it reaches the max, the top portion, right? So then if we go over here and we stop, if we turn off the valve, all that water that was stored at its max is now slowly discharging the water, right? So same thing happens with a capacitor. When you got a source connected to a capacitor, it's going to slowly start charging up till its max. And once that source is turned off, it's going to start discharging its energy, aka its charges that were stored inside, until there's none left, right? And that's pretty much it. That's how a capacitor works, and this is what capacitors look like in real life. Sometimes you got these big fat ones, got these tiny ones that almost look like an LED kind of, but they're not. And yeah.
And one more thing that's really important about capacitors is also that just the concept of a time constant. So capacitors, like Justin said, they charge and they discharge. So when they discharge, it's going to take some time. If you guys have taken physics, electromagnetism already, whenever you guys did that lab where you charge the capacitor and it charges quickly, and then after that you record the time, how long it took for it to charge fully, and then for the discharge it took a while. So that's actually pretty important, just knowing these behaviors and how they respond to current.
Right. So now our last topic is inductors. So inductors are measured in henries and can be noted by the capital H. And the way we calculate inductors in engineering is V is equal to L, which denotes the inductance, and we multiply it by the derivative of current over time. And we solve for current with 1 over the inductance times the integral of V dt, which is voltage with respect to time. So what an inductor does is it stores energy within a magnetic field, and the inductor opposes a change in current. So meaning if a current increases, the inductor will try and keep it from increasing even further. So with that being said, inductors in steady state, meaning they're a DC source, they act as a short circuit. So if you have a inductor connected to a DC source, it'll act as a short, meaning you can represent it as like a wire per se. So this is what an inductor looks like in real life. And if we use the water analogy for inductors, this pump right here, this pump right here is going to act as our DC source, and it's going to be pumping the water throughout this whole system. So here, this thin piping is going to represent our resistance, and this water wheel is going to represent our inductor. So initially, when the water is being pumped, it'll go through here and through here, but it'll stop right here for a certain amount of time. It just won't move, just simply because the water wheel is too heavy for the water to move at the time. There's not enough force to let the water to get through. So initially, the water will be flowing in through this branch right here and back into the pump. But over time, the water would be able to overcome this water wheel's weights per se, and it'll slowly start to move the water wheel until it gets faster and faster and faster to the point where this water will now start flowing through here more rather than this, since this is the path of more resistance, and this would be considered the path of least resistance. So the water pumping through would come through here and through here, but it'll mainly go through here just simply because the water wheel's turning so fast that the water doesn't feel like it's opposing its flow. So now let's say we turn off this water pump, right? Well, this water wheel is still going to be moving still, because I mean it's going to take a while for it to start slowing down. So water's still going to be flowing throughout, but eventually it'll start slowing down to the point where it stops and nothing will be flowing anymore. So this is pretty much a way an inductor works. An inductor is charged, and then it starts discharging its energy that it's stored in its magnetic field. And yeah, that's pretty much it. I think I saw some questions in the chat, so give me 1 second. Yeah, we got 2. I love that Ohm's law picture with the 3 little dudes. Thanks, Tariq. So inductors, capacitors, and resistors essentially slow down current. Well, resistors slow the current down. Inductors really don't do that in a DC source. Instead, if you have a DC source connected to an inductor, the current's going to want to flow through the inductor, because the inductor is going to act like a wire rather than an inductor. Because so capacitors and inductors are reliant on time, so their main functions are heavily used in AC circuits. Since AC has that sinusoidal graph, it can manipulate voltage and current over a specific time frame. So when you have a DC source, an inductor will act as a wire, and therefore the current's going to want to flow through the wire rather than a resistor, because there's no path of that's the least path of resistance. Sorry. And with the capacitor, the current doesn't want to flow through there because it's going to act as an open circuit, and with an open circuit, current does not flow through, since there's no way for the current to jump over to the other side. And we'll show you guys an open circuit later on.
And also, like a good way of remembering that for me is also like, so the big takeaways for capacitors and inductors is capacitors and inductors, they both store energy. Capacitors, they store through electric field, and inductors, they store through magnetic field. And also, when connected to DC current, they both behave in 2 different ways. With the capacitor, it acts as an open terminal. The best way to remember that is with that thing about the capacitor having 2 sheets, and in that open area, that's where the electric field's at. So just remember that if it's a DC source connected, then it's going to act as an open terminal. And with the inductor, if you look at the picture over here on the slide, they're all coils. So coils are just wires, just coiled up. And so just imagine that with a DC source connected, that coil just kind of gets stretched out and it turns into a regular wire. Just a regular wire with no resistors, anything. So it's just going to be a short circuit, and the current's just going to fly through there.
Yeah. Alrighty. So now we're just gonna show you a schematic, typical schematic of an RLC circuit, and we call it an RLC circuit because it's got a resistor, a capacitor, and an inductor. So here we have our voltage source, regular DC, and we got current flowing from the positive end, because remember how we talked about passive sign convention and conventional current. So we got the current going through the positive end and spreading out into this side and here. So it goes through the resistor. The resistor impedes the flow of current, so not a lot of current passes through here. And then we got our capacitor. Our capacitor has those 2 platings that Kevin mentioned, and that's why current in a DC source won't really flow in through this side, because there's no way for the current to jump from this end to this end with this gap in between. So rather, current's going to want to flow through here into the inductor, because the inductor, like Kevin said, is going to kind of like stretch out in a DC source and act as a wire, and then it'll flow its way back into the negative end. And that's pretty much all we have for you guys in our presentation. We have this little circuit here. If you guys want to solve it, it's just using Ohm's law. Let's see if I can zoom in a little bit for you guys. Damn it.
So you want to like run through this problem? So did you guys want to give it a shot and give you guys like two minutes to try and solve this problem? And then after that, I was gonna go through step by step how to solve that. But yeah, if you guys want to try Ohm's law on this circuit right now to find the current.
Yeah, so our voltage source is 10 volts, and we got a 10 ohm resistor right here. So you guys can just tell us the answer in the chat. Yeah.
Or through the audio, whatever you guys want.
Yeah. We got 1 amp, 1 amp. Yeah, that's correct.
Here we go. Well, I was about to do it, like, cause I got the camera right here. I was about to do it, but I was like, dude, they got it, man. I mean, it is pretty chill. So equals IR.
Oh, and by the way, if you guys want, you guys can simulate circuits on your own, and it'll make solving circuits a lot, I don't want to say, well, yeah, it'll make it easier, but it's also a good way to check if you're correct. So the program that I'm running is called Falstad. No, put it in the chat, and it's pretty easy to use. It's got different tools that you can use, like scopes, like an oscilloscope, multimeter. It's got different sources, so you can mess with AC, DC, you can mess with resistors, capacitors, inductors. It's got all these bunch of tools that you guys can use. And they already have preset circuits made for you if you want to learn more, and just right here in this tab.
So other than that, did you guys have any questions about any of the topics that we covered?
Yeah. Will you guys be posting the PowerPoint? I can try. I could do it through the Discord. By the way, is everyone in the Discord? We got C. Yeah. All right. So yeah. I'll be posting it on the Discord as soon as I can, and I'll post it as a PDF. So like that, it's easier for you guys to see.
Cool.
But yeah, do you guys have any other questions?
Any critiques? Anything that we could have gone over better? Any
Yeah.
recommendations?
Did we suck? Were we all right?
A little slower. Ah, dang,
Oh
hey, you just told
damn,
us.
dude, man. All right. Yeah, my bad.
Hey, we'll send you that PDF.
Yeah, we'll send you that PDF for sure. I'll post it as soon as we finish our workshop. But yeah, all right. Thank you for that. All great info though.